Hello everybody, super excited to be here today. My name is Miranda van Minnen. I'm a software engineer at Convoy, which is a Seattle-based trucking marketplace startup. I'm here today to talk to you about how we use TypeScript to define our service APIs. So to start out with, I want to talk to you about what kind of problem we were trying to solve. So at Convoy, when we started this project, our backend services were talking to each other with engineer-defined HTTP protocols. This kind of took place in a variety of ways. So sometimes they used GET, sometimes query parameters, sometimes there was validation, sometimes there wasn't, etc., etc. We wanted to standardize this, and we preferred RPC, which is a pretty standard message protocol. You can see how it works here, with using TypeScript as the validation layer and JSON to send it over the wire. Because of the different approaches in communication, it meant that our client and our server code was fairly hand-rolled. Updating or editing an API required you to update this code, as well as any callers. Unfortunately, that meant it was easy to make mistakes or forget changes. For example, change a route in 2 places, forget one, or update your typing in your server and forget to update the client. Basically, if you don't update the client and the server in the same way at the right time, you get errors, unfortunately. Another problem we had is that the existing recommendation for how to do the client and server code was to copy another server and then alter the code as you needed for your new service. Each service then wrote this code slightly differently, and no 2 services were exactly the same. Basically, it evolved over time. So we said, we've got a solution for that. It's a language called an IDL, or Interface Description Language, that can be used to describe a service interface in a pretty clearly structured way. It uses an independent, separate language to define the APIs and then generate the server and the client code so that the user doesn't have to. Most common IDLs support code generation in multiple languages as well. At this time at Convoy, we only used TypeScript, using it with Node on the back end and then with React on the front end. So we didn't need separate language generation, but we knew in the future this was a possibility. Some of the examples here for IDLs are Protobuf, Apache, Thrift, or Swagger. So what are the benefits that we could bring to Convoy by using an IDL? Well, instead of changing code in 3 places as a dev to edit or update an API, you can change it in 1, the interface, and the client and the server code will be automatically generated according to your interface changes. This also means, as an added benefit, that each service generates that code in a very consistent way, which means that the client and the server code for all of our services is pretty much the same. It allows our teams to develop the support and tools that we need much more easily because the services do things in the same way. So instead of developing a tool for one service, you can develop a tool for all services. In late 2018, we finally made the choice to use Protobuf with Protobuf.js, which is a library that could add TypeScript support for Protobuf. So we implemented it in a new service. It was pretty simple, and it worked great. We moved forward, and unfortunately, things just got hard. When we started implementing Protobuf in some of our more complex services, there were just problems everywhere. So what was our new problem that we were trying to solve? There were a couple cases where our solution fell apart. One was there were some assumptions that we made when using TypeScript's optional and required fields and defining how our services talk to each other. Unfortunately, these assumptions made it difficult to translate into Protobuf-only optional format. Another problem we ran into was that the main library we were using to add TypeScript support, Protobuf.js, had some significant bugs at the time around TypeScript, and activity seemed to have ceased. We couldn't get the support we needed to make them work, and without them working, we were going to have issues implementing this in our services. And then third, the community for TypeScript with Protobuf seemed really, really new. Looking around the internet, there was a lot of open questions, and nobody had answers. It looked like it was going to be hard to get community support for this effort. So we went back to the drawing board. Unfortunately, when we were looking at our options in early 2019, we quickly realized that this was going to be a hard decision to make. No matter how much research we did, there was no clear winner. There was nothing that said, this is the way you should do interfaces with TypeScript, unfortunately. TypeScript is still a fairly newer language as well, so the support was just not super wide. All of the approaches we found required a significant amount of additional work, and it took on a lot of unknown risk. You can see with this chart here, there's a whole lot of yellow, little bits of red, little bits of green, and they all kind of balance out to a wash. Even with a clear path forward, we knew this effort was going to take a long period of time, and we'd already failed once at this point, so we needed to mitigate our risk. Ultimately, we identified 3 major goals for what we were trying to accomplish. We wanted to lower the risk of blocking issues, focus on ease of migration, and make sure that the solution can be changed in the future. So in terms of lowering the risk, because the TypeScript community for the off-the-shelf IDLs seemed pretty limited, it made using one of these options fairly risky. It meant that we'd be supporting ourselves and potentially having to add all of our fixes that we needed to get these IDLs to work for us. For example, the last active library we had used seemed to have died. We thought about trying to create a solution and open sourcing it, but we realized that slowing or supporting external users would make us write that code a lot more slowly, and that was going to be a difficult thing for us. We also realized that if we were going to create a tool from scratch, it meant that we wouldn't have a community to rely on, and we'd have to do all that tooling by ourselves, which was a lot of effort and a lot of risk in a different way. Second, focusing on ease of migration and current usability. Migrations are hard. It's really hard to make a widespread change across the board. We figured the easier the migration is, the more likely we would be to migrate most of our users, understanding that a few just wouldn't be able to get there. In order to do an easy migration, we thought about codifying our existing patterns rather than coming up with new patterns. This felt like it would slow down our users the least amount because they wouldn't have to understand completely new technology. It should be pretty familiar for them. And then 3, make sure the solution can be changed in the future. We accept that we're not infallible. We don't know what the future holds. Hopefully, it means a much better TypeScript support system for commonly used IDLs. We wanted to give ourselves the option to say, you know what? Support out there is awesome. Let's grab something that somebody else is using instead of continuing to use something that we've created ourselves. So in this decision, removing any custom code that we create to make this work for us now and replacing it with the off-the-shelf solution is seen as a positive future for us. So you can probably get an idea of what decision we made based off of our risk areas, but ultimately we decided to create our own solution. We wanted to make this as simple as possible, so we wanted to take TypeScript, which was a known entity for us, use a small, simple subset of it, and then use that to create our own framework or IDL that codifies our existing patterns for RPC and asynchronous events. Filo IDL was born. Sorry about the naming. Unfortunately, we went the DOE, not the acronym, and we'd done internal branding for long enough before we realized the acronym was a thing that it was kind of irreversible. So how do we know we made the right decision? We don't. We set goals, we made decisions to the best of our ability, and we move forward. We move forward with the expectation that this may change over time and we may want to change our solution. And so because of this, we documented our entire decision-making process to remind us later why we made the decisions we did and how we made the decisions we did. All right, so now to the good stuff. How did we use TypeScript? So first off, we decided to create an IDL called Filo IDL. We wanted to be able to define both our asynchronous events and RPC interface using the same language. Then we also wanted to use a basic version of TypeScript. TypeScript was a known entity, and we wanted to use a basic version so that we could nudge developers towards simple interfaces and not prevent future operability between other languages. What this meant was no generics, no object unions, no any's. So how did we do that? As you can see here, there's a diagram of how we started with an interface declaration for both RPC and events, and we end with generated code for the client, the server, and the event files. In the middle is processing, and this is really what we're doing with our IDL. It's the part that I'm going to cover in more depth today. So there's 4 main stages to our processing, and it starts with filtering. One of the reasons that we have filtering is because we want to fail fast if users are using something they're not supposed to. Because we're using TypeScript, users have a tendency to say, I know this really cool TypeScript feature that I want to use in our interface. And we had to tell them really quickly, no, you can't. So we used the filtering stage to say, all right, run through the AST for the entire interface, and if any node type is not on our defined allow list, throw an error. This error let users know, hey, this is valid TypeScript, but it's not valid Filo. So please fix it. The second stage is parsing. This does the main heavy lifting of breaking down our interface into the logic that we need to render. Basically, it recursively walks the TypeScript AST for the defined interface, and it extracts any information we need from that interface. It then takes that information and adds it to an interim object. We can assume that PhiloIDL is valid TypeScript because it is a subset of TypeScript, which is convenient because we know that the code is compilable when it enters our parsers. So the parsers will store all of the data we need into an interim object. They're also stateful classes, so depending on what kind of node and where in the hierarchy they are, the proper parser is initialized and then used to extract the data and store it. It took us a while to figure out how to write a good parser. The first initial passes at this code were readable only by me, and that made it really difficult for anybody else to work in it. After a few iterations, we decided on classes, and every class had a either parse from symbol or parse from node function that would help to trigger a parse. The class itself that was initiated would store the information about the parse in the parser, and then all parsers had a getObject function that could return the expected data. Inside the parser may process the logic directly, or it may call other parsers. So, I've used the word parse a lot, but what exactly does that mean? Here's an example for a very simple input, an Enum parser. All right? So you can see in the upper right an example of an Enum, 1, 2, 37, numbers go in strange ways. How do we parse that down? So first we create a copy of the Enum parser class. Then we call parse from symbol, because we have a symbol for the Enum. It's a TS symbol, we pass it through, and the first thing it does is it says, okay, what's the identifier? Number is defined, it records that. Gets the associated node to the symbol. It gets any JS doc comments that are associated with that node, and then it iterates through each of the child nodes associated with that node and calls a key value parser on each of them. This means that the key value parser is doing most of the work for the actual key value pairs and parsing that information out. And the Enum parser is mostly responsible for the kind of top level information of the Enum. You can see an example here of a key value parser would be used 3 times for each of the key value pairs. And the first one would return an object that looks like key 1, node comments none, and value 1. Once that's complete, whatever is calling the Enum parser can call getObject, and it will be given an object with all the data needed to render the Enum. If that feels a little bit confusing, it's because it's really hard to figure out if you're not looking at the code, but here's an example of how it's broken down. An Enum like what is shown on the left gives us an object much like the one shown on the right. This is taken from a snapshot test, so it doesn't look like straight JavaScript, but it is just a simple TypeScript object. It stores the information about each of the value and key pairs, as well as the identifier and any comments that might be associated with the enum. So like I said, all of that data is stored in an interim object. Why did we decide to use an interim object? Well, having an interim object gives us a lot of flexibility of what's on either side of this parsing process. So as long as we can use whatever parsers we need to get it into the interim object, we can render whatever we want, whether it's TypeScript or Python or some other language. It also gives us the ability to replace the front chunk of it. If we decide we don't want to use TypeScript, we can use something else and still generate the same interim object and use our same rendering code. So not only is this helpful for us right now, but it gives us a lot of flexibility to change out pieces of our IDL in the future. Here's another example of turning something into an interim object. On the left, you can see a basic service called laundry service. We just have some very basic values in this, and then a quick shot of what it might look like if it was generated into an object, the interim object. You can see we've got the identifier of laundry, we've got some of the operations laid out, and of course, the interim object is quite a bit larger because it parses out all of the necessary data, so I can't show it all on one screen. The final step in processing is the rendering code. We need to render quite a bit of logic: client, server, types, environment, configuration, etc. To render the appropriate code from the interim object, we walk the interim object and use a series of functions to write whatever we need to the appropriate files. The most complicated portion of this logic is generating codecs, or encoders and decoders, for translating types into JSON and then back to TypeScript. It was really difficult to keep the recursion straight here, and validating that the result was what we wanted was very tricky. So how do we test this? Testing is really difficult. For the general server and client code, we mostly use snapshot testing and some validation helpers. You'd say, hey, produce the code. Did the code change from the last time we produced it? And do some of these things that we need to have there exist? For codecs, we would generate an encoder and decoder, take some sort of object, send it through one and then the other. So send it through an encoder, take the result of the encoder, send it through the decoder, and say, is this the object we expected to receive over the wire? Do we have extra parameters? Are they removed? Do we validate this properly? Those kind of tests. The most complicated part of testing this is for every typing feature you support, it had to be tested with every other existing feature. For example, if you add support for dates, you don't just need to test dates, you have to test that dates work in arrays. They work in multidimensional arrays, they work in indexes, that they work in a type reference, etc., etc. This is a mistake that we made early on, and it caused us to have bugs that we had to go back and fix because we didn't realize we'd broken something along the way when creating support for something else. So what did we learn? Filo Successes. On this project initially, we had about 3 engineers, and it took 2 months or so to release an MVP for the RPC side of things, and about 4 months for async. At this point, we had a very rough, very basic Filo IDL that was developed, and then it evolved over time, adding more support as we realized what was the bare necessities that we needed to make this work for our migrations. A year later, I'm happy to say that most of our services are using Filo to communicate with other services. It's built into our now service generator, so we don't have those copy-paste issues. And some of the remaining services are migrating over time. Another success is by integrating some good habits into Filo, we've increased our interface quality. One of those is no typing, or no any typing. This is something we fought a lot because people have a tendency to say, hey, I want to take this data, I want to dump it in my interface, and I want to just pass it through to this other thing. But unfortunately, that can cause a lot of problems. By preventing any typing, it's actually instigated some really great conversations with developers on why they're doing that. And we can figure out ways around that, or if there's alternatives to make things work like they need to have them work. We also have types that need to be declared locally. This is an issue that we had with constants being declared in one area and other services trying to import them in. It was really hard to keep them in sync, and there'd be discrepancies that weren't easy to track down. By having those types declared locally, it becomes much simpler for the services to keep them up to date, and it's easier for clients to understand what types are being supported by the service. We've also been discouraging string enums. This is a bad habit that's popped up in a lot of our code base, and it causes a lot of problems over the wire. So discouraging string enums and giving alternatives to people has helped improve our code base. One of my takeaways is discriminated unions are amazing. This is one of my favorite features about TypeScript that I learned during this process. Initially, when we created Filo IDL, we were kind of just guessing what objects were based off of what was inside them. This made the routing code for both the rendering and some of the parsing really, really complicated and hard to read. Once I figured out how discriminated unions work, we could really clean that up. You can see a great example here of a switch case statement that just says, hey, if it's this, do this. If it's this, throw an error. If it's none of these, something's wrong here, we don't support it intentionally. It allows us to give better errors for our users and kind of route our logic in a clean, simple way that is a lot easier to understand. My advice is learn discriminated unions, they're great. And then some other takeaways. Developing a feature like this in-house is risky and time-consuming, but it also gives you a lot of customization. For us, it was the right decision at the right time with the maturity level of our services, the staffing, and the speed we needed to move at. This isn't always the case, and I know it's a controversial decision. Especially with the maturity level of the community itself at the time we were doing this, it was a good move for us. Another lesson learned for me personally is compilers. I don't have a traditional CS background. I actually have a background in industrial controls, more hardware-based. And so I was kind of learning TypeScript and compilers at the same time. It's a non-traditional way of learning TypeScript, but I had a blast and I learned a lot of things. The AST viewer is a lifesaver. It took a little while for me to discover it, and before that, my coworkers would laugh because I'd have these diagrams written out on whiteboards just breaking down all the nodes and how it worked. So if you ever need to jump into the TypeScript compiler, AST viewer, it's great. Another thing we learned is that testing compiler code is tricky. It's hard to figure out what's going on in the inside. So our nature is to say, okay, let me test these little pieces. But with a compiler, you really kind of have to say, okay, I'm going to input this one thing, and I want to check to make sure the output is what I want it to be. How you figure that out and make it identify the problems in the middle is very tricky and hard to do clearly. We think we ended up doing it, and we're happy with the way it worked out, but it was definitely a learning process to get to that point. Another learning is writing parsers neatly is really difficult. I know I ended up refactoring the parser code 3 or 4 times just to get it to the point where my coworkers could be like, oh, this is clear. I understand what's in your head now. I think I can change that. I'm really happy with where they are now, but it took a while to get there. And then ultimately, never let our team name anything. We're really bad at it. That's why you end up with a software project named Filo based off of the DOE instead of the acronym. Here are some commonly asked questions that I get about Filo. Would we do it again? Would we develop our own kind of hand-rolled IDL in shop? Yes. I think it was the right decision for our company and our team at the time. The effort for what we were trying to do in standardizing personally our service-to-service communication at the time would have hit a ton of blockers using a standard IDL. There may be benefits that we could have pulled off if we had gone that route instead. I don't think it would have been easier. I think there would have been different pros and cons. But I think that by doing the in-house decision for us, we learned a lot about the way and along the way, and we were able to implement service changes in other ways that we wouldn't have been able to do if we'd used a standard IDL. And then another question is Convoy planning to open source Filo? The answer is not at this time. We believe that Filo, as of today, was the right solution for us at that time, but not necessarily long term. One of the main things we want is support for different languages, and we would prefer not to do that ourselves, custom. And so we don't want to open source something where we're not intending to support it for the long run, and we don't think it's a good solution for us in the long run. All right, so that's what I've got. Thank you so much for coming today and listening to me nerd out about our Filo IDL. If any of you want to talk about it more, I'm happy to talk to you about it. You can kind of see my contact information up there. And once again, thank you for joining me.